Okay, guys. Well, I will pretty much start now. Hi, everybody. Welcome to the MTH314 final exam tutorial. We are going to be studying some discrete math today. Before we get started here, how's everybody feeling? Let's see in the chat. How's everybody feeling for the exam? Is this a stressful one? Is this a not so stressful one? Like what are people's feelings? Horrible. I got a horrible. Scared, not bad, nervous, 50-50. Okay, so there's mixed feelings here. Yeah, good that you're joking. This guy, very bad. Yeah. Okay. Well, so there we go. So we'll go through some exams here, and so the plan is do both practice exam. I guess both doesn't actually have much meaning because there's more. Oh, can you see me right now? Is it sharing properly? Yeah, I think you can. Yeah. Okay. It was just Zoom all of a sudden showed me something. Something that was telling me that you couldn't. But anyways, so the plan is to first do the 2018 final. I might say midterm by accident. I say that a lot. Final, and then the 2012 final. But no one. But I don't have the 2012 final. So if someone would like to email it to me, then that is my email. So feel free to email that to me, and I will do that. Yeah, that's true. I should make the chat public. How do I do that? I will figure that out. Yeah, or the 2014 one. Yeah, I can do the 2014 one too. Start recording. How do I make the chat? I should really know this. Meeting in? No, probably security. Okay. Yeah, I'm not gonna worry about it too much, but maybe this gets one Google search. How to make chat open in Zoom. Oh yeah, I have the mega. Yeah. Oh, it's in the mega. Okay. If it's in the mega, then of course, then I have it. Yeah. Okay. Okay, I can't figure out how to make the chat open. It's not a button that's immediately available to me. So there he goes. Okay. So anyways, let's get started. I'll just do a couple notes here at the start. So I am recording. The video will be posted on my YouTube channel, which is just my name. It also says that on the bottom of the screen. I will have the chat open the whole time, so you can always just send me a message in the chat if you'd like to. And notes will also be posted in the description of the video, right? So that like the PDF that I'm writing on will be in the description of the video. Then you can find my notes for this course on my website, and there's two versions. There's one from like me actually taking the course, and then I wrote some notes just on the textbook after because I read the textbook after. So, anyways, that's the notes are available there on my website. When I took this course, there were no proofs, so this it's a little bit different. we had a completely different professor, but it was also discrete math, so it's very simple. A lot of overlapping concepts there. So anyway, so first do the 2018 final. 20 whatever. 20 something. Let's just do the 2018 final first here. So let's just get into it, and then we can kind of move on from there, right? Okay. So if anybody has any questions, you can always unmute, or you can type in the chat, and I will see in the chat. And I don't mind. You can do whatever you want. And if ever something's wrong, like my face is covering the side of the screen or something, just let me know. Like my face is covering this little square here, so I probably don't put anything important in there. But anyways, okay. So first things first, we're going to draw this truth table for this big expression, and it says use the truth table to. Yeah, can I skip this one? So I was asking. I'll do it quickly. It's not. It takes 1 minute to establish whether the following statement is a tautology or a contradiction. Either it's pre-midterm content, but let's go through it, right? So we have a big truth table here, and we want to just determine if this is always true or always false or some mixture between. And so the way we do this is we just start by getting all the lowest level pieces here, right? So we'd probably like to get Q and R first, right? So Q and R is, an and between Q and R here. So this is true, false, true, false, right? True and false here. Make false. This is false. This is false. This is false.
Q and R, not P and R.
Yeah. Oh, Q and R, not P and R. Yeah. Amazing start, as usual. True, false, 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 true, false, false, false. And there we go, right? So that's our first element there. And then probably the next element we'd like to get is the not P and Q. So you can either get not P on its own. We may as well just get not P quickly and not Q, right? Not P and not Q. It's good to just have a structured way. Once you have a structured way of doing this, it's really just following through with it. I get rid of that line. So anyways, this is just false, 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 true, 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 true. And then again we want to have why is this being difficult? There you go. And then we want to have not Q. The reason we want these things is you just look at the lowest level logical connective that you have there, right? So this is false, false, not Q is what I'm doing, right? True, true, false, false, true, true. If anybody's confused about that, just let me know. But it's mostly pre-midterm, so there you go. And now we start connecting these to larger things, right? So we'd probably want this not P and Q. It's probably the next thing, right? So not P and Q, or NQ, which is here, NQ. So these are the two things we're anding together. So true, false is false. True and false is false. False and false is false. False and false is false. False and false is false. And then, so Q here, true and true is true. True and true is true. And then these other ones are false here like that. Right? I'm looking at the right thing. Q and not P. Q and not P. Q and not P. And yeah. Okay. Good. And we have that. And then now, what do we have? Well, we're trying to get this whole thing as an expression at the end. Do we have all the constituent parts? Yeah, we do, right? So the next thing you'd probably want to get is this whole big expression here, right? So this is the Q and R, or not P and Q. And you basically just want to and. You want to or these two expressions, right? Take the or of these two. So the or of these two is going to be true, false, 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 true, true, false, and false. And then the last thing is just to and that with not Q. So take this and it with not Q. So I'm not going to rewrite it, but I'm just going to say the whole, the final thing. Just say dot here. Dot. So we're going to and this with this, right? So this is false. 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 And this is false. Okay, so we find that our final expression is always false. Therefore, the answer is that this is a contradiction. And that's that. So, first question, pre-midterm. That's pretty much that. If anybody has any questions, you can always stop me or ask in the chat, but that's the first one. Next question is prove the following using the standard set identities. So the standard set identities, I guess I can open it up on my website here. I'll open up my notes. So there they are. Let's see the standard set, or the set identities here. Here's some set identities, I guess, right? So yeah, we got a lot of set identities, and these are the sending me flying. Where's it sending There it is. So simple laws like commutative, associative, all that kind of stuff, right? Distributive is important. So the union distributes into the intersection distributes into the union, all this kind of stuff. These are just, the rest of these are a little bit self-explanatory. This other stuff is not particularly important. De Morgan's important though, right? So really the ones to focus on are distributive, associative, commutative. De Morgan is important, right? So De Morgan is the way, we know De Morgan from our electrical courses and all that. Yeah, absorption can matter, but doesn't particularly matter right now. And complements, all this. Set difference, that's important, right? So set difference here. And we're going to use this a lot. So you can write set difference as an intersection. And we're going to use that right now, right? So with this kind of question, we just, left-hand side, right-hand side, make the one turn into the other or make them both turn into something. So why don't we start with the right-hand side here, right? A union, well, B minus C. Right? B minus C is, we have B, we have C, right? And B minus C is this area here, right? It's everything in B, but take away the stuff in C. Well, another way to write that is that we take B, we intersect it with C complement, right? So we're saying everything has to be in B, first of all, and everything has to not be in C. So that's the union there, like that. And so we're taking the union with B intersect C complement. And I mean, we've done that. And at this point, what you could do is you could maybe distribute the A in, you could do other things, but how would you know to do that unless you see this other side, right? So maybe we'll start working on this other side. But that's just like one thing you could do to this right-hand side is to maybe just turn the subtractions into this intersection. So that was the right-hand side. And then the left-hand side, well, we do a similar thing, right? So this is going to be A union B minus C minus A, set difference of C and A. Well, it's going to be very similar. It's going to be C intersect A complement. C intersect A complement. And we have, I think someone's mic is on. Everybody check their mics. Got some mics on. There you go. So from now we have another set difference. So we could do that, right? So the set difference here, remember the whole idea of the set difference is that it's this intersect the complement of this, right? That's how we take the set difference of two things. So it's going to be A union B in brackets intersect and then the complement of this other thing, right? C intersect A complement. If anything's confusing there, let me know. I'm really just kind of applying, where am I? Really just applying this rule. What rule? I'm applying this rule, really. Just that the set difference is equal to that. This is equal to, I guess my face is covering that, isn't it? There you go. This is equal to B minus C. Okay, so now we're here, and we want to make it look like this. Right? Well, notice that there's kind of like two terms here. It's like you have two terms, right? That's a term, and that's a term. And here we don't have two terms, right? But maybe we could do that. Maybe we could turn this into two terms here, or we could maybe try to turn this into one term, but it's a little less obvious how we do that. So maybe here we can move back to this one, and we can distribute it, because I see an intersection between two things, and here I don't have that. So one thing I could do is I could distribute, right? I could say A union B intersect, that's the intersect that comes from there, A union C complement. Okay, these are looking very similar now. These are looking very similar. That matches. I just somehow have to argue that C intersect A complement is equal to A union C complement. And this follows pretty easily here, because I'll do it on the left-hand side. We have A union B intersect. Well, if we have a complement of an intersection, this is like a De Morgan situation. So for De Morgan, the C, the complement, hops down onto both the elements, hops down onto everything. It's C complement intersect a union, wrong word, in union, the intersect switches to a union, and A complement is just A, like that. So I applied De Morgan there. De Morgan. Whatever, capitalization there, but anyways. This is just applying the set difference rule, and this is De Morgan. And, well, now it's just the fact that we have the union is commutative. So we have A union B intersect A union C complement, and clearly they match, right? So we have LHS equals RHS for all sets. And this is true for all sets. And so even sets that are abstract, and we have weird sets like this identity is true. I don't know if we care for this identity, but it is true that this is equal to this. And you can, this follows from some set identities that we know. So, course of action here is just like if I'm teaching trig identities, it's just like do what seems like would be the next thing to do, which obviously that takes some practice to know what the next thing to do. But you see a minus, okay, I can use my minus law. I have a law for subtracting sets. Subtracting sets, I can use that too. Subtracting more sets, I can use that too. So if I have rules to subtract sets, then I probably want to do that because it's going to let me have a bunch of unions and intersections, and I have a lot of rules to do with unions and intersections. There's really only one rule for subtractions or for set differences. Yeah, so just going over it, right? I started with the right-hand side because it looked like the most obvious thing to me to do, right? Because we have this set difference. So I first applied the set difference formula. B minus C is B intersect C complement. A union that. But from there, it's not obvious what to do. So I started working on the left-hand side. I look at the left-hand side, and again, I turn this C minus A into C intersect A complement, which again just follows from the rule that we described here, which my face is covering, but there you go. And then from there, I use that law again, right? So I use the set difference law. I'll say SD for set difference. And then here, I use SD for set difference, right? Like the set difference law. And now I'm seeing that I have two terms here, something like this with a union, something like this with a union, and intersect between. I can make that happen over here by distributing the union into the bracket. Distributing the union into the bracket. Get two terms, get two terms. The blue highlights are the same. So I really just have to show that this second part is the same as the second part. And I use that using De Morgan and then commutative law. So it's important to know the laws that are available. And there's a lot of them, but really it's the ones that are going to show up are the set difference, like A minus B is equal to A intersect B complement. De Morgan, right? I'm not going to write all of De Morgan, but A union B complement is equal to A complement intersect B complement. And then I guess I am writing all of De Morgan. A intersect B complement is equal to A complement union B complement. So basically what I'm saying is that the complement jumps down on everything and switches that around. And then the simple ones like commutative and A complement is equal to A, stuff like that. Right? Those kind of simpler ones you should know, but these are the things I actually memorize for this kind of stuff. So there we go. That's our standard set identities with this. If anybody has any questions, feel free to stop me. Otherwise, I'm just going to keep going. So the next question is the following true for all sets A and B? If it is, give a proof. And if not, provide a counterexample. So what are we saying here? We're saying that the power set of A union B is a subset, is contained in the power set of A union the power set of B. Right? And this is not true. And so what exactly is a power set? And I'll give an example of that, of course, right? So let's just do an example of a power set, just a general power set here, right? So let's say we have a set A, which is 1, 2, 3. Then the power set of A, right? The power set of A is a set, itself is a set, and this set contains all the subsets of A. Any other set that is a subset of A is within A. So, for example, 1, the set which contains 1, that is a subset of A. It is contained, every element of this set is contained in A, which makes it a subset. Same with 2. Same with 3. Same with 1, 2. Same with 2, 3. And same with 1, 2, 3. 1 is an element of A, right? Just the number 1. 1 is an element of A. The set which contains 1 is not an element of A, but 1 is. And so this set, this is a subset of A. The following statement is true, as in 1 is a subset of A. Yes, I'd include 1, 3 in the power set. Yes, I would definitely include 1, 3. I just forgot to write it. And other than 1, 3, now that I wrote it here, right? Maybe I'll write it here. There's still one more I'm missing. Anybody have a suggestion? One more I'm missing? Other than 1, 3. Oh, someone said it already. The empty set, right? The empty set is a subset of all sets. It's always set there, right? Okay, so this is our power set. Notice that the power set contains the set itself, right? 1, 2, 3 is in there because that's a possible subset, is itself. So 1 is a subset. What does it mean to be a subset? 1, 2 is a subset because every element of 1, 2 is inside A. Is 1 inside A? Yeah. Is 2 inside A? Yeah. It's a subset. The power set is the set of all subsets. So now this is asking a much more general fact about power sets. And likely a question like this would be false because in general, it's not the easiest to prove something like this. I mean, how would you prove something? To prove something's a subset. Well, you'd have to prove that any generic element of this is also an element of this. That's what you'd have to prove. Any generic element of this is also an element of this. That's possible to prove it under certain circumstances, but it's better to just kind of try an example, right? So this is an example. I'm not claiming it's true or false yet, but I'm just going to do an example to see kind of play around with it and see what it is. So let's just take the set A is 1 and B is 2. B equals 2. Simple sets, right? And let's find all of these elements, right? Let's find the power set of A. Let's find the power set of B. Let's find the power set of A union the power set of B. And then let's find the power set. Oh, I guess, and then we need A union B. And then we need the power set of A union B. And I'm just finding all the elements of this. And then I'm going to ask, is that a subset of that? These are all sets. So let's fill this all in. You don't have to do 1, 2. 1, 2 is just kind of arbitrary. Could be whatever you want. Could have more elements, but just this is enough to show what I'm trying to show. So the power set of A is the null set, the set which contains 1, and that is it. Right? The power set of B is the null set, the set which contains 2, and that's it. And so then the union of these two is the null set, the set which contains 1, the set which contains 2. All right, I took the union of these two and got that. Okay, so I looked at that. I found my left-hand side, and I'm going to now look at my other side, right? So now I take the union of the two sets, right? So the union of the two sets is 1, 2. Union is just or. It's in this or that. Then I take the power set of A union B. So null set, always. Then each individual thing. Okay, 1, 2. These are subsets. And then 1, 2 is also an element of the power set. Okay, and then now I have to ask, right? I ask a question now, true or false. Is the power set of A union B a subset of P, the power set of A union the power set of B? In other words, is it true that this whole, okay, just copy it, I guess, that this is a subset of that? And what does everybody think? Is that a subset? Wait for a few answers to come in the chat here. Got a couple no's. And the reason it's no is because there's an element of this set that is not in this set. And so it's that, notably, right? So this is not, right? So I'll just say not, right? Not in, the right set. Let's say right set or larger set, I guess. But anyways. And so we can conclude from this that this is not true for all sets. We found sets where it's not true, so we can conclude that it's not a set. Yeah, so this is like a proof by counterexample, right? That it's not true. Yeah, if the question were the other way around, that then would it be true? I think it would be. Seems to make sense. I mean, here we would get true, but just because we get true this way doesn't mean it's always true. That's actually something to mention quickly. Is if we got that this was a subset, that this was this was a subset of the larger set, then we learned nothing. We didn't learn anything. That doesn't mean it's always true. It just means that we've proven that it was true for those specific sets. And that's what would happen if you had sets which were already subsets of each other, right? If A was a subset of B or B was a subset of A, okay, then you would get this fact that is true here. Okay. Proving that is a different thing, but that's not what the question is. The question is just, is it true for all sets? And it's not. And so you can kind of find this by playing around with it. Now, there's two things that could happen when you're on the test. Either it is true or it's not. So if it's not true, then playing around with counterexamples, you'll find a counterexample and it'll be false. If it is true, then you'll still play around with counterexamples, and then maybe you'll get a hint as to why it's true. Right? Because that's kind of the benefit of trying examples. You're trying to prove it wrong, and failing is part of learning why the fact is true. I'd suspect that on the test it would be false because it's a lot easier to mark, and also it's just more reasonable than proving something like this. In general, again, the way you prove something is a subset of another thing is you just have to arbitrarily show that any arbitrary element of this set is in this set. And by the defining feature of what this set is. Yeah, I have a counterexample to the claim that this is true for all sets. Someone asked, would this be an example of a counterexample? Would what I did be an example of a counterexample argument? And yeah, it would be a counterexample to the claim this is true for all sets. So someone asked, how would we prove it if it was true? So that's what I was saying before, right? So the other way around. Yeah, then you would just show that some arbitrary element of this set is an element of this other set here. Right? So you might start by breaking up what does it mean to be an element of this set? Well, it means that you're a subset of A union B. And then try to extrapolate from there to the other one. Yeah, the details of which, obviously I'm skipping over details. The details of which we can do, but it's going to be a little bit of a discussion, right? So if the y were on opposite sides, it would be right then. If the things were on the other side, if they were on different sides, then yeah, then I haven't proved it, but I mean, it matches with this example that we did, and I can see why it would be true, right? Because what's the problem? The problem with this this claim is that this will always have the union of A and B. I mean, yeah, you can just prove it here, right? You can say the A union B is an element of this, certainly an element of this. A union B, right, is not an element of this, right? Because if it was, then that would mean that A union B is in the power set of A, or A union B is in the power set of B. But that's not true unless A is already a subset of B. A is a subset of B, then that's in there. So you'd make a certain argument like that the other way. We can talk about it, but maybe let's finish this exam first, and then we can talk about that. Again, I would suspect that it would be something like this on the test, where it's a false statement, and you prove by counterexample. I think that's what you want to mostly focus on for this question. But yeah. Okay, so if everybody's good, I will keep going. Then the next one, it says prove or disprove the following statement, justify your answer. Oops. So the first step of this is understanding what it even says, right? So it's saying that there exists some y, which is a real number, such that for all x, doesn't matter what x it is, x squared plus y squared is greater than 100. So there is some y, there's some set in stone y that I can choose such that this is always true. So we can play around with it. Like what if I chose y equals 0, right? Then is it true that x squared plus 0 squared is always greater than 100? Well, no, right? Yeah, no, it's not true, right? Because this is 100. It's not always, x squared is not always greater than 100. It's greater than 100 in certain times, right? So this is not a valid choice for x. Someone said y equals 10, and this would be that, is it true that x squared plus 0 squared plus 10 squared is greater than 100? In other words, x squared plus 100 is greater than 100. And then, in other words, x squared is greater than 0. This is also not right, because this is not true. X squared is not always strictly greater than 0. It is equal to 0 when x is 0. So anything bigger than 10 would work, right? If I chose y equals 11 is a fine answer. X squared plus 11 squared is greater than 100. X squared plus 121 is greater than 100. X squared is greater than negative 121. Negative 21. This is always true. Always true. True. So what we did is we found a y such that this is always a true fact, that x squared is always greater than x squared plus 11 squared is always greater than 100. Because it's simple. If I choose y equals 11, then that's it. And that's what the claim is. The claim is that there exists some y such that this claim is always true. And yes, it does. Right? Let's put, not true for all XER. X equals 0. Yeah. Which is, so someone's asking, if I just said y equals 11, isn't that enough? That totally is enough, right? That's claiming. I'm just sort of arguing here why 11 works. Does R include 0? Yeah, definitely. R does include 0. Why did you decide to set a value for y but not x? Because we're claiming that there is a specific value for y that works for all x. So the for all x here is saying any x value. Right? Any x value works. So I can't lock down x because it's saying that this claim works for any x value. But there exists some specific y in R that makes this true. And so I had to lock in what that y is. In general, I don't have to lock in exactly y, right? But in here I could, right? Here it's possible to do so. The next claim is very similar. It says prove or disprove the following statement, justify your answer. But it's everything's the same. There exists some y ER such that for all x, x plus y is greater than 100. And it's very similar, so we have to think about, this is true. Think about, why is this true or false? Well, why was this true? This was true because x squared is always greater than 0. This relied on the fact, right, that x, oops, I'm changing colors too. What am I doing? There you go. This relied on the fact that x squared is always greater than 0, since x squared is always greater than 0. If we tried the same exercise here, trying maybe y equals 11, then we'd get x plus 11. Well, not 11. We can't use 11 anymore, right? Because we're not squaring. But if I chose, maybe I chose 100 here, or 101, then x plus 101 is greater than 100. X is greater than -1. This isn't always true, right? I'm basically asking, right? Is this always true? I guess maybe I should ask that. If I pick y equals 101, is the following always true? Always true. No. Is always true. By always, what I mean is for all x in R, right? For all x in R. And that's not true, right? If x is -10, that's not true. So the thing that we use in the previous case to prove that it's true is kind of the thing that's showing why this is false. This isn't true. Right? It's not true that there is some specific y that I can pick such that if I add any number to it, it'll always be greater than 100. Yeah, we'll let y equals -x. Yeah. Well, there's no, okay. So people are suggesting like an algorithm to find the other one here. So we'll talk about that. That is a part of it, right? Can you explain when do we use counterexamples or proofs for these kind of questions? Well, use a counterexample when you think it's wrong. When you think it's wrong, right? So you try to find a counterexample for it. And then proofs when you think it's right, right? So that's why here. So for here we use some examples, but not counterexamples. Okay, so then I'm getting some suggestions here that we can choose choose y based off of x. And there are cases like that, but is this a question where you can do that? Because there exists a YER such that, yeah, there exists YER. There'd have to be some statements here about like for each. So, yeah. You can choose an x. Yeah, x with a y. Just based off of the phrasing of the question, I would claim that this is false, right? That there is no y in the real number such that makes this always true, right? That I can pick for this statement such that it is always true. So to prove that, I would take the negation. So if I'm trying to disprove it.
But if it was -y plus 101, the y's would cancel and it would be 101 is greater than 100.
Yeah.
That would be an example of a value.
And that would be like there exists y in R for each x in R such that the following is true. But I don't know if you need a... Yeah, I'm thinking about it here. Exists y in R. Yeah, you're definitely right in if that's the phrasing of the way it's phrased, if it's meant to be interpreted like this, then yeah. But the way it's written makes it seem like we have to lock in the y at the start. There exists a y in R such that the following statement is true.
He would choose a y value and then be like, okay, is there any x value that can make the statement false?
That can make the statement false.
Yeah.
Okay. So we if that's how the prof interprets these kind of questions, then sure. So then
like I guess you choose a y value first, and then you see like
yeah, and then for any y value you choose, there is an x that can make it false.
yeah, that's what I tried saying.
Right. Yeah.
Like no matter how big the y is, there's always or no matter how big the y is,
big
there's
the
always
y
an
is.
x that can make that
false. Yeah. Okay. So then it's false. The overall statement is false here, that there exists some y such that this is always true. I get what people are saying, where you can like take x, choose y based off of x. And I definitely have done questions like that before. I mean, didn't we have a question like that in the midterm review that we did? Let's compare it to that. This question was our midterm. Yeah, here, someone's sending a midterm question here. Oh, yes on midterm, yeah. We'll show the negation is true. Yeah. Proving the negation. Yeah. So it's a false overall statement. Okay, we're on the same page. It's a false overall statement. Proving the negation involves choosing something. Okay, yeah. So the overall statement is false here, and we want to, disprove it. And so to disprove it, we're going to prove the negation of it. We're going to take the negation. So the negation of this kind of statement, all the there exists turn into for alls, and the for alls turn into there exists, and you flip this around too. So for all y-er, there exists an x-er such that x plus y is less than or equal to 100. And this is certainly true. For all y-er, there exists an x-er, x and r, such that this is true. And the way we do this is we choose a y. We choose a y. We choose an x, right, based off of y, right? So this is basically saying for each y in R, there is some x that makes this true. And in this position, we can just pick an x based off the y. Because we're not saying that there's a specific x that works for all y's. That's what we're saying up here. We're saying there's a specific y that works for all x's. But here, we're saying that for all the y's, you're able to find an x that makes this true. And you would do that by picking negative y. Right. So basically we lock in y. Let's say y locks into some number here, right? Y locks into something, some specific number. Right. If we choose x to be negative y, this will just cancel, and this is certainly a value that is true. Yeah, good question. Why are we picking negative y? You could pick anything. Anything that you can add to a number that makes it less than 100. Right? So if I have a number y, and I want to add something to it that makes it less than 100, well, I don't know what the number is, so I can't just like subtract 100. I don't know what y is, right? But what I can do is I can add from this side. I can add the negative of itself, and that would be 0, certainly 0, which will make it certainly less than 100. But it didn't have to be that. It could have been y, like y, negative y plus 1. And if I choose that, right, and then I use that to evaluate this expression, I have to ask now, if I make this choice for x, is the following thing true? X plus y is less than 100. Well, then I have negative y plus 1 plus y less than 100. 1 is less than or equal to 100. And there we go. I thought that x had to be a specific value, and it can't vary depending on y. It can. So okay, yeah. So it's the order that the order is the confusion here, right? So we're claiming that for each y in R, there exists a unique, that's not really the right phrasing, but a unique, there is some x such that this is true. The other way around didn't work. We're saying that for each y, there exists some y in R such that this is always true. But that is not true. So the order, which variable is getting the for all and which one is getting the for each, that tells you when you're allowed to lock it in. So like here I'm locking in that x is equal to negative y plus 1. In that case, right, I get this. And it's fine. It can depend on y. Because I'm just saying that for all y, there is some x that makes this true. For all y, there is some x that makes this true. There exists some x that makes it true. You can always pick a number x that will make the addition less than or equal to 100 for any y you choose. Yeah, there's always a way to pick it. There's actually infinitely many ways to pick it, but there's always at least one way, right, to pick what x should be to make the addition less than 100. So, I'm just doing +1 here just to kind of like show that it's possible to do it with any other form, but you can do it with just negative y. Since this is false, you're using counterexamples for it. So this is a different way. So this is false. So I'm not using a counterexample. I'm proving the inverse. I took the inverse of this. Right? I inverted this, and it became this. Now, this is true. So I'm trying to prove this to be true just directly. Okay? So I take the inverse of this. Could you also say x equals negative y as 0 less than or equal to 100 is also true? Yeah. Yeah, x equals, yeah, I have that here. X equals negative y. I just did +1 to show that like there are other solutions, but yeah, if I just pick x equals negative y, right, pick x equals negative y, then we just ask, right, is it true that x plus y is less than 100? Again, for all y, whatever y is, right? We have negative y plus y less than or equal to 100. 0 less than or equal to 100. Someone said, so taking the contrapositive, not quite. Contrapositive is where I have like an implication. I have like something, if this, then this, then I can kind of swap them around in a way. Not directly swap them around, but I can swap them around according to the contrapositive formula. No implication here. Yeah, right? So if I want to prove, if I have a state, someone's asking, can I explain what I mean by inverse, taking the negation? Yeah, these mean the same thing, right? So I have a statement like, it is raining, and I want to, prove this false. Then I take the negation, it is not raining, and I prove this true. And that's the same thing, right? So if I want to prove that it's false, that it's raining, I can also prove that it's true, that it is not raining. These are equivalent. It's nothing different here, but one's easier than the other in certain cases. It's the same thing. So yeah, what I mean by inverse is the negation. These mean the same thing. I'll post this recording immediately after the session. So yeah, so I've proven the negation. Therefore, the original statement was false. And there we have it. So I'll just write that here, right? I've proven the negation. Therefore, I'll put on the next line. Therefore, the original statement was false. I've proven that for every y, there does exist an x that makes this true, which is the opposite of this. Okay, that was took a little bit of discussion there, but hopefully that makes sense. I'll move on unless anybody has any questions they want to ask, but there you go. The next one here is the quotient remainder theorem. And whenever you use quotient remainder theorem, they're going to give you a hint. They're going to tell you what D value to use. The idea of quotient remainder theorem is that I can pick any natural number. Let's say I pick 3. Then every other natural number, or really integer, is either a multiple of 3, 1 above a multiple of 3, or 2 above a multiple of 3. And there's no other option. It's one of those 3 cases. So if I can prove each of those subcases, then I've actually proven my fact about all the integers. So the question says, use the quotient remainder theorem with D equal to 3 to prove that the product of any 2 consecutive integers has one of these 2 forms. Okay, so closed captioning is being generated. Okay, sounds good. So then the way we start this is we say, well, we select, we're taking the product of 2 consecutive integers. So let's say n is the first integer and n plus 1 is the second integer. Right? Well, let's break this into, we want to figure out if this has the form, a multiple of 3 or 2 above a multiple of 3. Even if they didn't say hint d equals 3, you could see that you need to use 3 because we're talking about multiples of 3 here. So suppose that n is a multiple of 3. Then we need to look at what n plus 1 looks like. What form this is in. Can it be written in one of these forms here? Well, we can do it. So we say that this is going to be 3k plus 1. And n plus 1 is 3k plus 1. Which is 9k squared plus, well, you don't really need to do that. You just need to show that it's 3 times an integer or 3 times an integer plus 2. Well, you can just take a 3 out of this, right? So 3k plus 1. And yeah, k is an integer. 3k plus 1 is an integer. So this is 3 times some integer. And so it is in the form 3k or 3k plus 2. But not every starting number is going to be a multiple of 3. So what if it's another case? What if it's 1 above a multiple of 3? Then what does n times n plus 1 look like? Well, it would be 3k plus 1 times 3k plus 1 plus 1, which is plus 2. Okay, so now again, we just kind of like, well, we can either try to factor out a 3, but we can't really factor out a 3 because we start getting rational numbers, and we don't know if those rational numbers will turn back into integers and all that kind of stuff. So we can just FOIL this out. Let's do it underneath here. So 3k times 3k, 9k squared, plus 6k, plus 3 more k, so 9k. And then 1 times 2 is 2. And now this, we can't factor a 3 out of it. But maybe we can write it in this other form. Is it 3 times an integer time plus 2? Well, I can factor a 3 out of that. 3k squared, 3k squared plus 3k plus 2. I just factored a 3 out of the first 2 terms. And yeah, look at it. There you go. So now that is an integer. So that means that this is equal to 3 times an integer plus 2. And that matches that form. So it's either of these. We have to match either of these forms here. And remember, any combination of integers is still an integer. The integers are closed under addition, multiplication, and negation as well. And that covers everything. Not division. They're not closed under division because, or however you want to, whatever you want to call division, right? Then you introduce rational numbers by doing that. But under these operations, just addition, multiplication, we're good. So then the last step, I said that in the first case, suppose that first number in our product is a multiple of 3. Then I said, well, it's not always that. What if it's 1 above a multiple of 3? Well, still, it's not always that. It could be 2 above a multiple of 3. Suppose n equals 3k plus 2. It could be 2 above a multiple of 3 or 1 below a multiple of 3. Well, then we have to, again, investigate what n plus 1 looks like. Well, it's going to be 3k plus 2 times 3k plus 3. Again, my goal, why not assume 2k plus 1 and 2k for even and odd? You totally could do that, but there's no way you could then write it in this form. The question is saying make sure that the product can be written in this form as 3k and 3k plus 2. If you chose 2k plus 1 and 2k, then you wouldn't be able to get 3k and 3k plus 2 as your forms at the end here. You have to choose 3 as your divisor. Good question, though. In general, you totally can choose 2k, 2k plus 1 when you're doing general proofs for using quotient remainder theorem. So again, our goal here is just to write this either as a multiple of 3 or a multiple of 3 plus 2. I can factor a 3 out of that. So I'm going to say 3, 3k plus 2, k plus 1. You know, the integers have this property of distribution, so you can factor out. Does a remainder have to be less than 3? Yeah, absolutely. So 2, 1, and 0 are all less than 3. Those are the remainders in quotient remainder theorem. So 2, 1, and 0. I did 3k plus 3 because it's n plus 1, right? So n is 3k plus 2. So then n plus 1 is 3k plus 2, 3k plus 3.
What about the 2?
This 2?
No, and the one below. Like, how do you factor that one out? Like, how you factor? Oh, I see what you did. Never mind.
Like
Got
this
it.
here?
Yeah,
From
no,
the
I got
2.
it. Never mind. I missed
Got
it. Yeah.
All right, beautiful. So then that is an integer. And so clearly our number is in the form 3 times an integer, which is the form that we wanted. We're done. Those are the only 3 cases. Yeah. 3k would work too. Yeah, I did 3k right here. Oh, yeah. Like you can call this 3k. Yeah, it doesn't really matter. Sure, it's different k. But it's the same. But really you want to show these 3 cases. These are the 3 cases because n is certainly one of these 3 cases. And those are exhaustive cases. Right? It's in one of those forms. If the form was 4k plus 1, you would do 4 cases. Yeah, if the form was 4k plus 1, then you'd have, like, if it asked you for those forms, or if this d value was 4, then for 4, every number is either a multiple of 4, 1 above a multiple of 4, 2 above a multiple of 4, or 3 above a multiple of 4. But there's no number that is, not one of those cases. There's no number that is not one of those, but also 4 above a multiple of 4. Because 4 above a multiple of 4 is, once again, a multiple of 4. All right, so every integer is either one of those cases. So it wouldn't make sense to go now and say, suppose, this wouldn't make sense. What I'm doing right now doesn't make sense. To say, suppose n equals 3k plus 3. Because that's 3 times k plus 1, which is, k is some integer. K plus 1 is still some integer. It's just 3k naught. Well, that's same as case 1. I've already proven this case. So if d equals 4, we do 4 cases. Yeah. If d equals n, you do n cases. So we're done at this point with this. Okay, so that's a quotient remainder theorem question. Let's do some induction. So induction is a really important property we have of the integers, the natural numbers. Question there? No? I didn't. Heard voice for a second. Then it went away. All right. So yeah, the induction is a very important property of the natural numbers that they do this essentially, and it's you've seen this analogy before, I'm sure, but it's like dominoes. What do I need to know to know that all the dominoes fell. Let me draw a couple dominoes here, right? There's two things I need to know. To know, like, you know, let me write this out, right? What do I need to know to be sure that all the dominoes fell? First thing I need to know is that, you know, the first domino fell. And the second thing I need to know is that all the dominoes are spaced correctly. And that's all I need to know that every domino in my little row fell there. We use the exact same logic with this. Right, so this is called the base case, and this is the inductive step. Right? And with those two facts, the natural numbers can be, you know, have this inductive property that we can prove facts about it. This is the whole concept of induction. And there's strong induction, which is just slightly different, but we'll talk about that in the next example, but it's really the same thing. So let's do it here. Using mathematical induction, show that this is true. This formula is true, that 4 times a number is less than 2 to that number for any integer greater than 5. And it has to be integers. You know, induction only works with integers here. I don't know if induction is some sort of induction for real numbers. I don't think so. I mean, I can't. Yeah, I can't see how that would work. So then we start off by proving the base case. Okay, which is part 1 here. And the base case is that it works for 5. Right? So if it works for 5, this is like the first domino falling over. Is it true that 4 times 5 is less than 2 to the 5? Well, you can just literally check it. Right? Yes. So the first domino has fallen. Okay. The next one is the inductive step. Right? Is assume that domino K has fallen. In other words, that this statement is true for n equals K. So assume statement is true for n equals K. Oops, K. That means that we know the fact that 4K is less than 2 to the K. This is a fact that we know and we have to use. We now need to show that logically this implies that you know, the statement is true for n equals K plus 1, the next domino. So assume that the kth domino fell. Show that logically the K plus 1th domino had to have fallen as well. And K is arbitrary here, right? K is anything. This is the making sure they're spaced correctly, essentially. And so we need to show that 4K plus 1 is less than 2 to the K plus 1. That we just have to show this using this fact. Okay, so how are we going to do it? Well, we're going to start with our, start with what we know. And we know that 4K is less than 2 to the K. We have this fact and we need to use this fact. Adding 4 to both sides. Okay, how do I guess I should be so quick to jump to that, right? So we're trying to show this. We have to get to this. Somehow from this, we have to logically conclude this. Well, you see, distributing this in here, we would get 4K plus 4. So maybe I'm going to add 4 to both sides to kind of make at least one side look more like this. So, this takes a little bit of creativity here, but we get 4K plus 4 is less than 2K plus 4. We still know this is also a true fact, and this matches that, right? This matches that. 4K plus 1 is less than 2 to the K plus 4. Okay, we've shown this, but that's not exactly what we want, right? But if we could maybe somehow show that this side is less than, is less than 2 to the k plus 1, then maybe that would be helpful. And then that would prove our fact here. And we can do this. The way we can do this is, remember for a second, is that this is certainly less than 2 to the k plus 2 to the k. How do I know that? Where did I pull that from? Well, what did I do? All I did is I changed the 4 to 2 to the k. We know 2 to the k is greater than 4, since k is greater than 2. Right? If this is true as long as k is greater than 2. We know k is greater than 2 because we're doing 5, right? We're doing things bigger than 5 here. So I guess we should say that, right? For n equals k, k is greater than 5, or equal to 5, I guess. So since k is notably greater than 2, we know that 2 to the k is bigger than 4. So by replacing 4 with this, we certainly get a larger number. We certainly get a larger number here. And the rest kind of just falls from this. So that's the same as 2 times 2 to the k, which is equal, just straight equal. And that's the same as 2 to the k plus 1. Like I'm dot, 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 like that. And we're done, because we showed it. We did it. We showed that that is less than that, which is what we're trying to show. We've shown that all the dominoes are spaced correctly. And we use the fact that we were given right there. Here, someone's asking a question. Like in that. Here. We have 2 to the k still. Yeah, the green one. Oh yeah, where did that 2 to the k go? Well, I mean, I turned this into this. Right? Because like x plus x equals 2x. So blah, blah, blah plus blah, blah, blah equals 2 blah, blah, blah. So I just turned that into 2 times 2 to the k. No problem. Where did you get the 4 from on the right side? On the right side, this 4? Or the same as this 4, right? I added 4 to both sides. That's what I did. I added 4 to both sides. Like compare this equation and inequality and this inequality, I added 4 to both sides. And the reason I did that is because I wanted to match this, because that's 4k plus 4, right? So now I have 4k plus 4. Okay, that's getting some progress there. Why did I change the addition to multiplication? Yeah, I understand that kind of looks confusing, but it's not. I'm not really saying much there. I'm saying 2k plus 2k is, I'm not saying that that's 2 to the k times 2 to the k. I'm not saying that. I'm saying that that is 2 times 2 to the k. And that, right? That maybe seems weird, but it's just, yeah, it's just like x plus x equals 2x. So I'm doing the same thing as that. Could you explain again why we did 2 to the k plus 4? I'm confused why I did that. Yeah, that really is the key step here, right? And the reason I did that is because that's what 2 to the k plus 1 is, right? 2 to the k plus 1 is 2 times 2 to the k, which is 2 to the k plus 2 to the k. But how would I think about doing that step here? And the reason is because I know for sure, what I'm trying to prove here is not equality. I'm trying to prove inequality. I'm just trying to show that that is smaller than that. Not that it's equal to that, but that is just smaller than that. So if I can show that that is smaller than some middle step, which is quite easy, right? I add 4 to both sides, and I show that that's smaller than some middle step. And then I can show that that middle step is smaller than our big step, the big value. Then I have transitivity here, right? Transitive, and that must be smaller than that. And that's essentially what I did logically here, right? I said that 4 to the k plus 1 is less than 2 to the k plus 4. which is in turn less than 2 to the k plus 1, transitive here, that must be less than that. This is just like our middle step, middle value. And I did it in 2 steps, right? I showed that this was less than this. Maybe I'll highlight here kind of what I did. So showing this was here, it's just that, right? And then showing this was like that section. I don't want to mess it up too much, but it was that section. And this is how we kind of prove something about some inequality here. And there you go. So that's done. Proved by induction. We did the inductive step. We did the base case. So this is true for all n greater than or equal to 5. The logic is this domino logic here. Okay, so hopefully that's making sense. Anybody has any questions? Feel free to let me know. Otherwise, I'll move on to the next example. Wait, here's someone asked something. Can we set n to be anything, or is it always n equals k plus 1? Yeah, you always set. Yeah, you always do this exact kind of structure. You just assume that it works for some n equals k, and then you prove that it works for the next one, which is k plus 1. You could also say assume that it works for n equals k minus 1, and show that it also works therefore for k. Sometimes that's a little easier, but it's often not easier. It's often better to just do it like this. Yeah, so we set n to be k at the start. Always, that's like, we assume it works for some value. Show that it must then work for the next value. That's like showing that the dominoes are spaced correctly. Assume that the kth domino falls. Assume that the kth domino falls. Show that the k plus 1th domino must also fall. Fall being that the statement is true. Okay, I will move on. No problem. Let f of n be a recursive sequence defined as follows. Boom, lots of stuff going on. For n greater than or equal to 2. Prove using strong induction that f of n equals 2 to the n. Okay, so what's strong induction? If this is induction, what's strong induction? This is induction. Strong induction is the same thing, but instead of showing that the first domino fell, we show, the first domino fell. The first few dominoes fell. Dominoes fell. All the dominoes are spaced correctly. Slightly, yeah. That makes it seem like the only changes, okay, so the analogy, doesn't perfectly work, but that makes it seem like the only changes in the first step. There's a change in the second step too, and we'll have to talk about that, but this is essentially what strong induction is. And use that to show that all the dominoes are spaced correctly. Maybe a better way of saying this, instead of all the dominoes are spaced correctly, if all the dominoes fall up to the kth domino, then the k plus 1th domino will also fall. A little bit more technical than I wanted my analogy to be, but that's the analogy. So that's the idea of strong induction, is that we have a sequence falling, a sequence of dominoes falling, rather than just one domino. So here we just verify the formula for the base case here, right? For at least for that it works for these first couple. I mean, you do a couple for strong induction, right? So for step 1, we do our base case, and we just verify that it works for, f of 0 would be 2 to the 0, which does equal 1. Yep. F of 1 should be 2 to the 1, which does equal 2. Yep. And f of 2, which is 2 to the 2, which does equal 4, which works. Great. We did the base case. So now we do the inductive step. The inductive step is assume the formula works for all n equals k for all k less than, how should I say it? For all n less than k. That's how I should probably say it. For all n less than k. So assume that all the dominoes fell up to the kth one. So that means that we know that f, let's just say I, equals 2 to the I for all I in, k minus 1, k minus 2. That's a weird way to say it, but for all k, let's just maybe write it out here. For all I from what? From 0 to k. So f0 equals 2 to the 0. f1, so on, right? All the way up to fk, I guess less than equal. fk is equal to 2 to the k. So assume that all the dominoes fell. Show that the formula must work for n equals k plus 1. And we do this using the recurrence relation that's defined here. So let me take a screenshot of that and bring that down here. So we're assuming n is greater than 2 here. And we're also assuming, k is also, technically we're assuming it's strictly greater than 2, but whatever. We're assuming k is greater than 2 here. So assume that, let's say k was 2, then assume it works for everything up to that would be a valid assumption. And then we want to show that therefore it must work for 3 according to this recurrence relation. We're doing it more generally. So so I essentially just do what it says, right? So this fn plus 1, I guess let me show what I'm trying to show. This is what I'm trying to show here. This would probably be a good thing to. I'm trying to show that fk plus 1 must equal 2 to the k plus 1. That's what I mean. That's what I mean for the formula works. That's what I mean. For the formula works, it means that fact. So that's what I'm trying to show. And the variables doesn't normally matter here. So fn plus 1 equals, we just rewrite this in terms of k's. I think that will make more sense if I just rewrite this in terms of k's. Right? Doesn't really matter. I'm just relabeling. It's just a k, but I think it's going to be less confusing if I do that. So why don't I do that quickly? I just relabel this in terms of k's here. I'm not spend much time doing this, but just give me a second. So then the k, we have k. Maybe my labeling could have been better there, but anyways. So fk plus 1 is equal to, well, we know that fn, or fk, is equal to 2 to the k. So this can be 2 times 2 to the k. And for k minus 1, this is the point of strong induction. I don't just know that it works for k. I know that it also works for k minus 1 and k minus 2 and so on. So this is going to be 2 to the k minus 1 plus 2 times 2 to the k minus 2. I know that the formula works for all of these. And now it's just some algebra. Right? This is 2 times 2 to the k minus 2 to the k over 2 plus 2 times 2 to the k over 4, just over 2 squared. Factor a 2 to the k out. It's just 2 minus a half plus 2 over 4. This is 2 to the k times 2, which is 2 to the k plus 1. And so there we go. I've shown it. I've shown that fk plus 1 equals 2 to the k plus 1. Why isn't it 2 times 2 to the k minus 1? It's just from the form. There's no 2. There's no 2 there. So just based on that, which was given. Right. And that's it. I've proven that this formula works for this recurrence relation for all k greater than equal to, well, for all k greater than equal to 0. Because I manually checked 0, 1, 2, and then I showed how it works, that it must work for further ones just based off of strong induction. Glad to hear. Someone understands. That's good. So that's strong induction, which is very similar to induction, but you have more of an assumption, more that you have to check, at least, for this kind of stuff. All right. That is strong induction. If anybody has any questions. Can you explain the last part again regarding k plus 1? Yeah, like this section here. So like fk plus 1, I'm just using the formula. I'm rewriting the formula. I know that my formula works for all values less than k, or k or less. Right? So I know that fk is 2 to the k. I know fk minus 1 is 2 to the k minus 1. I know fk minus 2 is 2 to the k minus 2. So just plugging all that into the formula, doing some simplification, I can show that that must be equal to 2 to the k plus 1, which is what I was trying to show. K is arbitrary. So there we go. All right, that is that. Again, if anybody has any questions, feel free to stop me. Next one is a relation. So let R be the divides relation for the following set. Which would be better to use for strings? What do you mean, which one would be better used for strings? Like strings, like the data type? What's the string question? Like the, is a type of induction question? An example of like an induction question? Okay, I'm unfamiliar. Inductive proofs on strings? Something like this? Yeah, this is, well, not this course, so probably not that helpful. But yeah, I'm unfamiliar. So there you go. Okay, so let R be the divides relation on the following set A, which is all of those values there. That is that the relation means that if X is an A and it's related to Y, which is also an A, only if X divides Y. That's what the divides relation is. So we know that it's a partial order. So partial order is just a way for us to have a set. It's a relation on a set that lets us order that relation in, not a complete way. Not everything is comparable, but there is some kind of comparison you can make between elements. So we don't need to show that's a partial order, but state 3 properties and their names that are needed for the relation to be a partial order. So those 3 properties are just, things that are here. So the first thing is that all ordering needs to be reflexive. Reflexive. Okay. So this just means that x divides x for all x in A. Right? This is the idea of reflexive. Then we have anti-symmetric. This is important, right? So anti-symmetric means that if we have x, for example, is greater than y, greater than equal to y, and y is greater than equal to x, if these are both true, then the only way this is possible is if x equals y. So I'm using the ordering because we're talking about a partial order, but it's the divides relation. Right? So anti-symmetric means that in the case of a divides relation is that if x divides y and y divides x, then this implies that x equals y. No need to prove it. We're not proving it. We're just stating the properties here. Just as an example there. It's the idea of anti-symmetric. Okay, so there's our anti-symmetric, and then the last one for an order like this, any kind of ordering needs to be transitive. Okay, and in terms of our divides relation, it just means, well, it means what it means in all cases, but let's just write it for the transitive. So if x divides y and y divides z, this implies that x divides z. For all of this is for all x, y, z in A, like that. And those are the three properties for something to be a partial order. For something to be a total order, there's an additional property that everything needs to be comparable to everything else. Right? That is, it's possible to be compared to everything else. So, in other words, everything's kind of in a long line, essentially, right? There's no kind of interconnections there. Well, there's interconnections, but it's always clear which one's bigger than the other. That would be a total order. So there's our properties. The next one is draw a Hasse diagram. So Hasse diagrams are ways to draw partial orders. And we remember what our set is. That's important. And our relation. Our set is the following numbers, and our relation is the divides relation. So you want to start with what can divide a lot of things? What is related to a lot of things in here? 2 is related to a lot of things. 2 can divide a lot of stuff here. Yes, exactly. Someone said 2 in the chat. Exactly. 2 can divide a lot of stuff here. So 2 should go on the bottom. And what's the next smallest thing that it can divide? Well, 4. But where does 3 fit into this? Well, it's not true that 2 divides 3. This is not true. It's also not true that 3 divides 2. It's just separate. Then the next thing that 2 divides is 6. But we have to ask, does 4 also divide 6? No. So it's its own kind of branch here. I'll just put it in the middle here. It's its own kind of branch. And then we ask, does 3 divide 6? Yeah, it does. So there you go. That's where 6 fits in. And then we go to the next thing. We did 2, we did 3, we did 4, we did 6, 8. Well, 2 certainly divides 8, but 4 also divides 8. And so you take the top one. You take the furthest one. That's what the Hasse diagram. That's what makes it a Hasse diagram. you take the top one. Transitive edges are implied. You don't draw an edge like that. They're just implied. But, 3 doesn't divide 8 and 6 doesn't divide 8, so no other lines there. 12. Well, 2 does divide 12, but 6 also divides 12. 4 also divides 12. 3 divides 12. A lot of stuff dividing 12. 8 does not divide 12. So kind of like the highest it goes is kind of like there. 6 divides 12 is good. 3 divides 12. That's implied by this kind of transitive edge. That's implied there. 4 divides 12 is nowhere to be seen. So we got to draw an edge like that. 4 does also divide 12. Finally, 24 is divisible by the most amount of things, and it should go on the top here. 8 divides 24, and 12 divides 24. 4 also divides 24, right? 6 divides 24. 2 divides 24. 3 divides 24, right? Everything divides 24, so it's at the top. But it doesn't divide anything. That's why there's nothing above it. And that's our Hasse diagram. Sure, it's the same as what I drew before. Yes, it is. Yeah. So that is our Hasse diagram. Now, using this diagram, we need to answer a couple questions. So let's answer those questions. Yeah, just go up a little higher here. Go. Why do we need a line from 4 to 12? Because without it, then we're not ever showing that 4 divides 12. Because 4 divides 12. That's really it. 2 divides 12, but that's already in this line. Okay? But 4 also divides 12. So to show that this partial order, that 12 is in a way bigger than 4. 12 is also bigger than 3, but it's kind of like that. And the sense of bigger here is not like direct, like greater than, less than. It's divides. That is the sense of bigger. That's why it's a partial order. And it's a partial order because, it's like, 4 is bigger than 2 in the sense of divides, right? 4 is bigger than 2. 24 is bigger than everything else. But comparing 2 and 3, well, in the sense of divides, they're incomparable. So that's why it's a partial order. You can't, some elements you can't compare. 8 and 12. I can't compare that. I don't know which one's bigger. In the sense of the divides relation. Okay, so let's maybe answer this. There we go. So when answering the next 4 parts, write none if no elements have the required property. The maximal elements, the minimal elements, the greatest elements, and the least elements. So the maximal elements are elements that are kind of like, they're like local maxes, right? So 24 is a local max. Right? It's greater than everything that it is comparable to, it is greater than. Minimal is everything that it is comparable to, it is less than. Well, that's 2 and 3. Right? 2 and 3. So everything, right? So let me repeat that, right? So for maximal, we're just asking, looking at the elements here, which elements have the property that for everything that it is comparable to, it is greater than, and minimal is the less than. Greatest is asking which element is comparable to everything and is greater than everything. Well, that's still 24. Right? 24 is greater than 8, 24 is greater than 12, 24 is greater than 4, 6, 2, 3. Minimum elements is asking what elements are comparable to everything and less than everything. Well, 2 seems like it could be a candidate because it is less than everything except 3. It's incomparable to 3. So 2 doesn't work, and for the same reason 3 doesn't work. So there are no minimum elements. Is it possible for greatest elements, greatest meaning the thing, to not exist? What if there are duplicates? Yeah, totally possible for greatest elements to not exist. Yeah, it'd also be because 2 doesn't relate to 3. Exactly, that's why. So it's totally possible for greatest elements to not exist, just like it's right here, minimum or least elements. Also, it doesn't exist in this case. There you go. No problem. There we have it. So that's that question. That's the Hasse diagram and then our descriptions here. Let's say I had 1 instead of 2, then 1 would be the answer for the last part. Yeah, absolutely. Let's just throw 1 in there. 1 divides everything, right? Now 1 is the minimal element, the only minimal element, and it is also the minimum element. It's minimum because it is comparable to everything and it is less than everything. Yeah, you can easily tell the minimum if there is only 1 minimal. Yes. Yeah. That makes sense. Why is it none? Someone's asking, right? Because without the 1, 1's not there. 1's just my addition. Then there is no element that is both comparable to everything and also less than everything. 2 is less than everything except 3. 3 is less than everything except 2. Well, not 4, but 3 is less than most things. But it's not comparable to everything. So it doesn't have a chance to be the minimum or the maximum. So there can be a single maximum and 1 minimum. Every time maximal and greatest elements will be the same. Not necessarily. You could have multiple maximal elements, right? But then you'd have no minimum. So I guess if there's a single one, then yeah. Well, not necessarily. That you could have a more complicated diagram that would have more things. So it's important. Just the words I'm saying are the important thing. There can only be 1 maximum, 1 minimum. That sounds right. Sounds right to me. Let's Google it. Can there be? Yeah. If there was 2 greatest elements, that means there are 2 elements that are comparable to everything and also greater than everything. But there's some contradiction there. Can there be only 1 greatest element of a partial order? Yeah. So for a partially ordered set, which is a set with a partial order, while there can be at most 1 maximum and 1 minimum, there may be multiple maximal or minimal elements. And then for totally ordered set, the notions of maximal and minimal coincide. Anyways. So yeah. Yes. Correct. All right. There's that. So that's that question. Yeah. Trick question because it says elements plural. Yeah. Well, yeah, exactly. There, you gotta know what you're talking about to answer these questions. Okay, next question. So let A be the set of students writing this exam. The relation R on A is defined as follows. If X are Y, if and only if they're sitting in the same row. X is in the same row as Y. So is this relation reflexive? So the first thing you want to ask is it true? Is the following true? If is true or false? True or false?
True.
Yeah, it's true. But what I'm going to say here is Tom. Let's just give a name Tom. is sitting in the same row. Sitting in the same row as Tom. Same guy, not two people with the same name, same guy. You know, when I read it like this, it's clearly true. It's the same guy named Tom, right? Tom is sitting in the same row as Tom. So this is clearly a true fact. That's what reflexive means, right? That an element is related to itself through this relation. Yeah. Oops, wrong color. So that's that one. Is this relation symmetric? Well, I'm going to do the same kind of example, right? So that means something similar. I'll just type it this time because I'm a little slow at writing. Tom is sitting in the same row as Bomb. Does this imply that Bomb is sitting in the same row as Tom? Is this implication true? And that is true, right? That they're sitting in the same row. Tom is sitting in the same row as Bomb. Let's just say they're in row K. Then this other statement is the same thing. So yes, also symmetric. Let's just say implication. Implication is true. So yes. And then the last one is a transitive. So we're going to do a similar thing here, right? Tom is sitting in the same row, as Bomb. And Bomb is sitting in the same row as Wom. Does this imply that Tom is sitting in the same row as Wom? And yes, it does imply that, right? If we just think about the rows of people, this one, maybe a little picture might be helpful, but like, let's say these are all the desks, right? And then I don't know why I made so many columns. So let's say this is Tom right here. Tom is sitting in the same row as Bomb, and Bomb is sitting in the same row as Wom. Does that mean that Tom and Wom are in the same row? Certainly. Yes. Implication is true. And there's that. That's that question. Got one more question here. Anybody has any questions about this? Let me know, but that's essentially it. Question says, does there exist a simple graph with vertices of degrees 1, 1, 2, 3, 3? If it does, give an example of such a graph. If it does not, prove its non-existence. So whenever you know the vertices, can you do something on recursion if there's time? Yeah, I mean this was a recursion question, but if there's another question, then we can do it. We'll finish this question and then we'll have a few more minutes after. Or I don't know if we will, but we'll see. So does there exist a simple graph with these vertices? Well, whenever you're given a set of vertices, to verify if such a graph does exist, you use the handshaking lemma or whatever, handshaking theorem, or whatever you want to call it, or the first theorem of graph theory, which is that the sum of the degrees of a simple graph must be even. this is a fact that we have. So 1 plus 1 plus 2 plus 2 plus 3 plus 3, which is 10, is even. Therefore, such a graph can exist, and a simple graph can exist. And so let's just draw it out. Let's draw 5 vertices, maybe like this. And I want to have it with this. So there are 2 vertices that have a degree of 1, which means they're only like touching one thing, right? So let's say that's that. This is going to have a degree of 1. Let's say this one also only has a degree of 1. Okay, so I got the 2 1s. This is a 2, but I do need to connect it to these, so probably is going to be a 3, right? It's going to be a 3 here. But then I want to get a 2 and a 3. Well, I'm a little bit stuck, right? Because I can put a 2 here, but this is another 1, so this didn't work. So maybe we got to backtrack a little bit here. Maybe both of the 1s can't be connected to the same node. Maybe that's a 1. That's 1. What do we have now? 1, 2, 2, 2. And what do I need to do? I need to change 2 of them to 3. Well, what if I connect these 2? That's a 3, and that's now a 3, and there we go. So I've drew such a graph, simple graph that has these properties: 1, 1, 2, and 3, 3. Would there be a case where the sum of the degrees is odd? Yeah, it's just not possible. It's not possible to have a simple graph where the sum of the degrees is odd. So if they were asking, does such a graph exist, then you would say no, and the reason is because of the whatever you want to call it, handshaking lemma, or I forget what it's called now, but the name of this theorem. The fact that the sum of the degrees of a simple graph must be even. That's what the fact is. Okay, so that's that. And yeah, so let's take a look at the next one. So this is the last question on the practice test. Does the following graph have a Hamiltonian or Eulerian? This is a typo. It's a different mathematician, but that's not a circuit. It's Eulerian circuit. If it does construct such a circuit, if it does not prove that such a circuit cannot exist. So for this kind of graph that we have here, right? Let's first look at the Eulerian one. An Eulerian circuit is
we
one
actually stopped before Eulerian, just so you know.
Oh, you did. You didn't do this in the.
No, our last lecture we stopped right at Hamiltonian and didn't make it to Eulerian.
Oh, but isn't it before? Let me see. Someone sent me the slides. Oh, I don't know. It maybe different prof got to a different thing, or maybe did your prof just skip it? Because I think in order on the slide, maybe we're talking about different slides, but in order on the slides it goes.
Actually, on his announcement, it says including Eulerian circuits. So exam should be on Eulerian circuits as well.
Okay, so I'll talk about it. Up to including. People are telling me here, Euler's included, not Hamilton. Sounds good. Eulerian's the easier one. So an Eulerian circuit is a circuit, which means a closed path, closed loop of vertices or edges, I guess, which visits every edge exactly once. So you want to find a path that visits every edge exactly once. So let's say, for example, we start here, right? And maybe we go use a different color. Right? We start here and we go. Still not a good color. Use a bigger pen. There you go. Start here. We go like that, and then like that. Well, we want to visit every edge, right? So once, exactly once. So I'm a little stuck because I can't. If I go here and I go here, then there's no way I can get this edge again. Question? Anybody? Someone gonna say something there? Okay. So I can't go like that. So what if I start here instead? Well, I'm kind of again stuck because I can't go down this edge Well, I can. But now I've blocked off this edge. So I'd have to go through it now. But okay, I guess that's actually fine so far. And now I'm here. But I have no way of getting back. So the circuit part means you get back to where you started. So just trying it out, it looks like there's no Eulerian circuit. And this is true. Right? This is a true fact. And the way you'd prove this is, just remember here, I just copied it, or I copied it earlier. I'll just paste it in here. Oh my God, why is it going off the screen? They're most two, yeah. Well, this is what really, I don't know if this, I don't know if you're gonna do Eulerian path as well, but a graph has an Euler circuit if and only if the degree of every vertex is even. Euler path is just a path that visits every edge, but doesn't go back to where it started. Circuit goes back to where it started. So it only has a circuit. It has a circuit if and only if the degree of every vertex is even. Well, that's not true. Degree 3 right there, right? Degree 3, degree 3. So there is no Eulerian circuit on this graph. Circuit on this graph. Yeah, path and trail are interchangeable. I think so. I don't know if I'm familiar with trail, but we can just look this up. Graph, trail. Trail. Trail is an open walk with in which no edge is repeated. Yeah. In the context of Eulerian stuff, it is interchangeable because no edge is being repeated. Okay. Well, it is 8 o'clock, so unfortunately that is our time for today. But hopefully you guys, found it helpful to go through this and getting another explanation of these questions. You should totally be able to do the other exam. It's, I read through it. It's basically identical. Do I have past exam reviews on YouTube? Yeah, I did also do a tutorial for this class last winter. So there's also a video up for that. Some similar questions, but different questions too. So that's on my YouTube channel. You can all go take a look there. Someone said, can I scroll back down? Probably to the graph one, I guess. But yeah, so that's all for today. I won't do any more writing, but I will, stick around for a few minutes. If anybody has any questions, I'll just, I'll stop recording though.